Hello everybody. In this video we're going to draw the Lewis dot structure for, what is that, formaldehyde actually right there. The first thing we're going to do is write down the different types of atoms that we have. We have hydrogen, we have carbon, and we have oxygen. Next we'll need their electron configurations. If we refer down to our table here, we can find the valence portion for all of them. Here's oxygen, here's carbon, here's hydrogen. And that would allow us to see that hydrogen's is 1s1. Carbon's has a helium core, 2s2, 2p2. And oxygen has a helium core, 2s2, 2p4. They're all main groups, so we just need to sum up these subscripts here to find the number of valence electrons for each one. So every hydrogen's giving me 1 valence electron. Every carbon is giving me 4 valence electrons, and every oxygen is giving 6 valence electrons. Again, that's always going to be true. Hydrogen's always going to be a 1, carbon's always a 4, oxygen's always a 6. Now we need to figure out the total number of valence electrons that we have. We have 2 hydrogens. That's our only multiple, so we're going to do 2 hydrogens times 1 electron for each one of those, plus the 4 electrons from carbon, plus the 6 electrons from oxygen, giving us a total of 12 valence electrons to work with. The next thing we need to do this time is to decide which of these is going to be our central atom. Typically, we have 2 criteria to kind of decide this. The first one is that hydrogen here can never be a central electron. It always has to be a terminal one, because it only takes 2 electrons in that 1s orbital, so it can only form a single bond. It'll never form a double bond. It'll never have like lone pairs or anything like that. So we know hydrogen has to be on the outside. The choice is between carbon and oxygen, and typically what we're going to do is we're going to put the least electronegative one in the center. We could go look that up in the table, but we can also know just from its position on the periodic table, oxygen here is further to the right, and this is the direction where electronegativity increases, so oxygen is more electronegative than carbon, which is going to cause us to put carbon in the center. That means that that carbon is bound to a hydrogen, it's bound to another hydrogen, and it's bound to an oxygen. Now if we consider hydrogen here, he has 1, 2 electrons, and that's all the electrons hydrogen ever wants. So these guys are already happy. They have the equivalent of their full octet when they just have 2 electrons. So we're not going to place any more electrons on these hydrogens. We do need to figure out how many more electrons we need to place in general, though. So I had 12 electrons in the bank. I formed 3 bonds worth of electrons at 2 electrons apiece. This means I have 12 minus 3 times 2, negative 6. 6 electrons left still to place. And what we're going to do with these electrons is we always want to start by filling out the terminal atoms on the outside, which kind of makes sense because what we're doing, if we're placing the least electronegative one in the center, we're placing the more electronegative ones on the outside. So it makes sense that we're going to assume that they start having electrons because they just have more affinity towards those electrons. So I'm going to need to place 6 electrons. I can't put them on the hydrogens, so I'm going to place them on oxygen here. Now I can go through and do my count. Once again, hydrogen 1, 2, happy. Hydrogen 1, 2, happy. Oxygen 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's happy. Carbon 1, 2, 3, 4, 5, 6. Carbon is not happy yet. Carbon needs somebody to share electrons with them. And the hydrogens don't have any to give, so it has to be coming from oxygen here. We'll imagine this lone pair coming down to form another bond there. If we rewrite that result down here now, and we can redo our count. Once again, the hydrogens are happy. From oxygen's perspective, 1, 2, 3, 4, 5, 6, 7, 8. He's still happy. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Carbon is now happy, and this is the structure for formaldehyde that we would expect.